Hello, everyone. I'm Yiyuan Zhang, and together with my team from the Chinese University of Hong Kong and Tencent AI Lab, I'm excited to present our work on enhancing transformers with unpaired data from various modalities. Our paper, Multimodal Pathway, Improve Transformers with Irrelevant Data from Other Modalities, explores innovative ways to leverage multimodal information. Let's delve into the potential of our research multimodal pathway. Let's continue by reviewing the evolution of data paradigms in model training. Initially, we leveraged datasets like ImageNet with a singular modality, training and validating on tasks like classification. Then, the second paradigm shift we see in training AI models is cross-task transfer learning within the same modality. After training on ImageNet, models demonstrate strong pre-training adaptability by performing different tasks, such as detection or segmentation. This versatility is a testament to the transferability of learned features, but our research doesn't stop there. We push boundaries further by training models on multimodal data, such as Leon 2B for similar tasks. This introduces complexity and richness in the learning process. And finally, we ask, what happens when we introduce multimodal irrelevant data? That's the crux of our paper, as we'll soon explore, yet our research suggests there's untapped potential in expanding beyond single modality, which brings us to our innovative approach with multimodal unpaired data. In our quest for advancement, we ask, can we make these diverse datasets, spanning images, point clouds, videos, and audio, work in concert for training a better transformer network, even though these data are unpaired? The answer is a resounding yes. Our approach is clear: to create a synergy between these modalities. By leveraging the inherent strengths of each, like the spatial richness of ImageNet, the depth information in ShapeNet's point clouds, dynamic context from ActivityNet videos, and the temporal patterns in AudioSet sounds, we aim to enrich the learning process. This cross-modality complementary patterns of modalities sets the stage for our multimodal pathway, enabling models to glean comprehensive insights from seemingly unrelated data streams. As we delve into the intricacies of our approach, let's revisit the concept of structural reparameterization. This technique has proven advantageous for multi-branch learning, allowing for complexity without increasing inference costs. When applied to multimodal contexts, it demonstrates significant benefits, enabling each branch to specialize in different data streams without overwhelming the model. Most crucially, this methodology aligns seamlessly with transformer architecture, setting the stage for our proposed innovations in leveraging multimodal irrelevant data. This alignment allows us to harness the power of transformers in a way that is both efficient and effective. Here we introduce the crux of our paper, the multimodal pathway. Taking inspiration from Jeff Dean's concept of pathways in AI, we envision a framework where distinct streams of modality-specific data can interlink and complement each other. Our proposed architecture is not just flexible. It's designed to harness the unique strengths of each modality, facilitating a complementary augmentation process. By applying this to the versatile transformer architecture, specifically vision transformers, we implement cross-modal structural reparameterization, enabling our models to extract a richer set of features and insights across diverse datasets. Our architecture extends the vision transformer (VT) model by incorporating cross-modal structural reparameterization. This means each transformer block is not tailored to a specific modality, yet can communicate and enhance the other blocks with the advancement from other modalities, effectively sharing diverse modality patterns and context. Imagine a scenario where the texture details from images, the depth cues from point clouds, and the temporal dynamics from audio are collaboratively interpreted to enrich the model's understanding of a scene. What sets this apart is our emphasis on flexibility. Each modality branch can operate independently or in concert without imposing additional computational costs at inference time. The result is a synergistic model with the capacity to learn not just from relevant data, but also to draw context and improve performance through seemingly irrelevant data streams. Let's turn our attention to the backbone of our multimodal pathway, the transformer architecture. We've customized it to handle different data types: video, images, point clouds, and audio spectrograms, each with its processing stream, illustrated here by distinct color-coded paths. At the heart of each path lies the transformer's multi-head attention mechanism, which we've adapted to attend not just to intramodal features, but also to intermodal relationships. This allows each modality to inform and refine the processing of others. Following the attention layer, we have the normalization and MLP blocks, which are critical for stabilizing the learning and allowing for complex function approximation within each modality stream. The key innovation here is how these modalities interact at different layers of the architecture. We orchestrate this interaction through the use of shared projection and linear computation units, effectively enabling a fusion of insights across modalities. The beauty of this system lies in its simplicity and efficiency. The pathways remain within the bounds of the transformer architecture, ensuring that computational costs remain manageable while the cross-modal learning potential is maximized. We detail the technique of cross-modal reparameterization, a pivotal element in our architecture. The process starts during training, where the output of two linear layers from different modalities is combined with a learnable parameter, lambda, allowing the network to dynamically adjust the contribution of each layer's output. Now, let's focus on the weights, W and W prime. During training, these weights are individually learned, but come inference time, we combine them into a single set of weights, which is the sum of W and lambda times W prime. This mathematical unification means that we've essentially baked the cross-modal learning directly into the network's parameters without any additional inference cost. It's a clever optimization that preserves the separate learning pathways during training, but consolidates them for efficient execution during inference. This technique exemplifies the efficiency of our approach, achieving a simple and effective multimodal integration while maintaining a very small computation. Here we see the multimodal pathway transformer, or M2PT, our customized extension of the vision transformer designed to handle multiple data modalities. This diagram illustrates the flow of data through two distinct yet interconnected modalities, for example, images and point clouds. On the left, we have the primary pathway for images as target modalities. It follows the standard vision transformer structure with the sequence of operations: query key value, QKV, projection, multi-head attention, normalization, and the MLP blocks. On the right, the auxiliary modality pathway processes point clouds. It's been pre-trained on point clouds with a mask reconstruction task to provide rich, spatially coherent features. The innovation lies in the cross-modal reparameterization, represented by the blue lines, connecting the two pathways. During training, we allow the model to learn representations across these modalities, enhancing the feature space with modality-specific characteristics of each. The blue arrows signify the data flow, where learnings from the point cloud processing enrich the image, modality processing, and vice versa, allowing the model to leverage the strengths of one modality to compensate for the weaknesses in another. In essence, M2PT is a cohesive network architecture across modalities that's greater than the sum of its parts, capable of extracting a deeper understanding of modality-specific information by considering it in a broader multimodal context. Let's take a look at the empirical evaluation of our multimodal pathway's effectiveness. The results are compelling. Across different datasets representing diverse modalities, we see consistent improvements. For ImageNet in 1K, we observe a 0.4% to 0.9% increase in top 1 accuracy. The Kinetics 400 K400 dataset shows even more pronounced gains with up to a 5.7% improvement in top 1 accuracy. Moving to 3D data, the PartNet shows a remarkable 3.8% to 5.7% boost in mean intersection over union MIOU, a significant metric in 3D object segmentation. In the audio domain, using AudioSet, we recorded an uplift in top 1 accuracy ranging from 0.6% to 0.8%. These enhancements underline the core strength of our multimodal pathway. It not only allows individual modalities to benefit from their intrinsic data characteristics, but also to cross-learn from auxiliary, seemingly irrelevant modalities. This mutual benefit underscores the robustness and versatility of our approach, positioning it as an important step in multimodal learning. Delving into the specifics, this table presents our results in image recognition tasks across different settings. Compared to the baselines, our approach shows a significant boost in performance. In the pre-trained setting, M2PT Point achieves a top 1 accuracy of 83.9% on ImageNet, which is a notable improvement of 0.7% over the MAE baseline. Even more impressive, we see a 3.4% increase in fixed accuracy settings. This trend of improvement is mirrored in complex tasks on MS COCO and ADE20K, where we see increases in AP box, AP mask, and MIOU metrics, respectively. From the scratch setting, we observe our method outperforms the standard VIT, underscoring the effectiveness of incorporating point cloud data, with improvements of up to 7.1% in tune accuracy on ImageNet. Our experiments yield clear results. The multimodal pathway markedly enhances performance across different modalities. Notably, in 3D shape segmentation, the M2PT model shows substantial gains in MIOU scores. For video and audio recognition, our approach consistently outperforms the baselines. The takeaway is striking. First, multimodal pathway advances in modality. Complementary knowledge, integrating point cloud data via M2PT leads to the most pronounced improvements, reaffirming our hypothesis that leveraging larger modality discrepancies can yield better performance. Meanwhile, for 3 different modalities of image, video, and audio, point cloud is the best auxiliary modality to support other modalities. That's all. Thanks for watching. We have open-sourced our code and models at GitHub. You may scan this QR code to get the code.